Good morning, and welcome to Container Days. It's not a very specific name. Maybe I'm here to discuss the history of Tupperware. No, worries, I'm not. I mean, I can't come up with a better name. It's not like Operating System Virtualization Days would fit easily on a sign. So we'll take what we have. Let me start my camera here. So my name is Jeff Victor. I work for Oracle Corporation. I used to work for Sun until Oracle bought Sun. So I've been doing the Solaris thing for a very long time and the virtualization thing for a slightly shorter time, about a decade. And my big claim to fame is being the principal author of a book on virtualization, which you can find at fine online retailers. We do have a Solaris 11 version of the book coming up. And according to Amazon.com, it's due November 19th. I don't know how they picked that day, because I didn't tell them that day. So we'll see what happens. Through this, I'll be talking about virtualization concepts, especially applied to containers, and the timeline, some of the history in here. And I asked Kir Kolyshkin to join me to fill in some of the history and concepts that he is more of an expert at than I am. So thank you, Kir, for accepting that invitation. So yeah, this is what we'll be talking about. This will be various things interspersed to make it a little more interesting. I will be talking about the differentiation between operating system virtualization, which we shorten to containers, and virtual machines. This will not be a highly technical talk. I'll warn you about that up front. There is a lot to say about the history of containers, but it's not very technical. Also, I will be here all day. I will not be here tomorrow. I have to go back. But I'll be here all day, so if you see me and you have some questions about containers, especially applied to Solaris, let me know, and I'll be happy to answer your questions. So the history of containers, as is the history of virtualization, starts quite a long time ago, back around 1961, where this little college about 200 yards that way wrote an operating system they called CTSS, the Compatible Time-Sharing System. One of the first time-sharing systems that was written, and it was one of the first things that allowed multiple people to use one computer at one time. And if you were, if your company had a computer, you were lucky. So you had to schedule time on that computer with the batch operating systems that were available back then. So this was a big step forward in making computers easy to use and making them more practical. It had a number of serious shortcomings, so people identified those. And the U.S. government, through the Department of Defense, their DARPA, the Defense Advanced Research Projects Agency, funded a competition and asked for groups to propose new ideas for a new second-generation time-sharing system. And GE submitted a proposal. They ended up winning, and that ended up becoming an operating system called Multics. And then some of the guys, after that project was finished, went to AT&T, and they created something called Unix, and then a bunch of other important things happened, and then we're here. So I'm done. Another little organization called IBM also submitted a proposal for the next generation time-sharing system, and they submitted a batch operating system idea. Apparently they didn't get the memo that this was supposed to be a time-sharing system. So they didn't win. And they were very surprised by this. So stinging from their defeat, they regrouped and decided to approach the idea of multiple people running programs on a computer at the same time from a different angle. They decided, well, we like this batch operating system kind of thing. We like this running one program on the machine at a time. Can we make it so that one person can run a program on a machine at the same time but have multiple machines in the machine? And that's how virtualization was born. They didn't call it virtualization. They didn't call it virtual machines. They used the word guest and the word host, which was new and interesting. So they came up with this project, which ended up being called CP40, CP for Control Program. That was the word they used for what we would now call a hypervisor. They came up with the word hypervisor later on. CP40 is because they used a Model 40 System 360 mainframe to do that. There was only one of those ever. It was just a research project, but it was successful enough that they productized it into CP67. And so that was the first product that had virtual machines, as we know them now, running on it. So this was for the CTSS ran on that, an IBM 7094, and this was a 360 mainframe part of it. And then CP67, it evolved over time to become VM370, VM-CMS, and other mainframe virtualization products. But that's where all this stuff came from. And along the way, IBM wasn't the only group thinking about virtualization. There were various research projects going on, research scientists working on this concept. In 1974, two professors, Popek and Goldberg, wrote a paper that was published in the Communications of the ACM in 1974. And they came up with what I call the three laws. They didn't call them laws because they weren't really. It's just a little inside joke. And as with those first three, I then later added two more to make the three laws. Theirs were equivalence, resource control, and efficiency. Equivalence meaning that they realized that in order to have effective virtualization, a program had to run the same in a virtual machine as it would on bare metal. And that was a new concept at the time. We sort of take it for granted now. But that was the concept of equivalence. They also realized that if you're going to put multiple people on a machine, especially if they think they have the whole machine to themselves, then you need resource controls to make sure that one person doesn't hog all the physical resources of the machine, take up all the CPU time, all the RAM, to allow everyone to make forward progress with their software. And efficiency, they said that the dominant portion of processing of a program has to run at roughly the same speed it would on bare metal, or the same speed on bare metal. They realized that there are going to be some efficiencies with most forms of virtualization, but they use that phrase, the dominant portion. Now, back in those days, especially in the days of batch operating systems, security was the door and the key to the door, because as long as you could keep people out of the room that had the punch card reader in it, then you had a secure machine. Now we have this nifty thing called the internet, so security is a big issue. So security is a big issue for virtualization. And lastly, the least like a law, administrative observability. This is not required. This is a nice to have concept. the concept that from one central place you can look into all of the workloads in all of the virtual environments to see what's going on in them. This is very hard to do with virtual machines. This is not that hard to do with containers. So this is one of those advantages that containers have over virtual machines, that ability to look into the processes. So if you're responsible for the whole machine and there's a problem, a performance problem or other, then it's nice to be able to look into what everyone's doing to see what's going on and who's causing the problem. So that nice introduction then led to what I called the Dark Ages, where not much happened. This was a time period when most of the computing industry was focused on two things: clock rate, increasing clock rate as much as possible, and making systems as small and as cheap as possible. And so some companies that I won't name for obvious reasons really went with the one person per computer model, and did a good job with it. They were very successful with that, that's a good thing. But in the meantime, in here, not much happened with regards to virtualization. So somebody thought of this concept of a virtual file system tree that would be part of the whole tree, and they called that a trooted environment. That was created for Unix version 7 in around 1979. That was then ported to other versions of Unix, and Bill Joy ported it to BSD4, which then became more widespread that way. 1991, somebody just used the word jail to refer to one of these things, and from that, someone come up with the word jailbreak. But nothing new there. Java Virtual Machine, the first that I know of, the first virtual machine that didn't have an analog in the physical world. So it wasn't, let's virtualize an existing machine, let's virtualize something that doesn't even exist. And then something which many people would not call virtualization, but partitioning, Sun's dynamic domains, that was take a big computer and isolate it down to the power grid, isolate some of the physical resources, some of the CPUs, some of the RAM, some of the I/O cards, make that a domain with a copy of an operating system running on it that was completely isolated from the others, so that if anything bad happened in here, it wouldn't affect the other ones. So partitioning has some strengths there in that level of isolation. And with the dynamic domains, you could even shift the border back and forth between the boards to grow a running domain while it was still in production and shrink some other ones. But that was about it for that 25-year period. So let's talk a little bit more about the different kinds of virtualization. I've been using this diagram. I keep modifying it, but I've been using this for almost a decade now to discuss those different kinds of virtualization. Over on the left-hand side, partitioning, where you have the best isolation. So you have more isolation as you go farther that way, but the least flexibility. If you want a program to use a little bit more CPU power, and you have those partitions, you can't do that. You can't give it a little more power. Over on the right-hand side, we have, for Solaris Zones containers, more flexibility but less isolation. And in the middle, you have those virtual machines that use a hypervisor. So here, you can see in this diagram the partitioning and the separate physical resources with virtual machines. There's different implementations, different features with the different implementations, but you always have a hardware, pool of hardware, a hypervisor that manages it, and then these different virtual machines that are these fictional constructs, pretend computers. And on the right-hand side, OS virtualization containers, where you have one operating system instance and multiple virtual operating systems inside. Most flexibility here because at any time, the operating system can give just a little bit more of some resource to a process up here that needs it. And you can consider these as just a set of processes that have some shared characteristics. So very flexible because you can do all that in software. Of course, the advantages over here, like I said, if any one of these fails, the rest of them keep running. Here, if one of these crashes for some reason, it doesn't affect the others. But if the hypervisor crashes, then all of the guests are going to come down with it, which is similar to here. If the operating system fails, then all of the guests come down with it. So if you're configuring for high availability, you need to take the different availability characteristics of these models into consideration to get to the level of availability that you want. Oh, wow, way ahead. Good. So that leads me finally to a definition. As I mentioned, a container or zone is a collection of software processes unified by one namespace. So that's one Etsy hosts file, one Etsy password file for users, one set of printers, one similar DNS, LDAP. All these naming systems unify all the processes in one container, but can be different in another container. This is, I'm of course speaking generally. A specific implementation of containers might do things a little bit differently. You might have one unified namespace. I would call that less of a container. But they all share access to one kernel. So all of them are making system calls into that one kernel. So the kernel has to, of course, know about this stuff and know what to allow and what to forbid. So the kernel has to know this process is allowed to use this device, but this other process is not. And then different implementations of containers distinguish them from each other. Usually, the rule is two containers should not be able to communicate directly in a way that two machines wouldn't be able to communicate. So they should still be using network semantics to talk to each other and not have some covert channel that is different, because that usually leads to security issues. And that goes back to that fourth of the 5.3 laws. So some of the advantages of containers. Typically, they leverage a mature operating system. So Solaris, Linux, many operating systems that have been around for a decade or more, the features that are in there can easily be leveraged in a implementation of containers. Compared to virtual machines, containers are very lightweight. So a virtual machine is going to have its own kernel, which is going to take up RAM. It's going to take up CPU time. Other resources, containers don't have that. They all share that kernel, so you just saved some RAM right there. Because you don't have to boot a full kernel when you're booting a container, containers typically boot very quickly. And it can boot in just a few seconds, because all it is starting up a few processes. And that's easy to do. Containers, unlike virtual machines, where the hypervisor usually is software running on a CPU, that takes up CPU time. That CPU time not being used by a workload. So hypervisor right there creates performance overhead. Hypervisors also have to usually get involved with any I/O, because if you only have a couple of I/O cards, a network card and a fiber channel card, and you have a bunch of guests sharing those, the hypervisor has to make sure that the right guests are doing the right things across those I/O cards. So that's more time the hypervisor is spending on the CPU, using up CPU cycles. Also with virtual machines, the hypervisor has to go and flush the CPU caches to get all of one guest's data out of there so that the next guest to run on that core can't access that data in cache. So there's more performance overhead. Containers don't have any of that. So there should be no overhead. I was part of a team this is back 2008, part of a team within Sun. We were comparing the performance overhead of various virtualization technologies, and I did the performance characterization for zones. And we used CPU benchmark, memory benchmark, network benchmark, storage benchmark, and some other composite benchmarks. And for every one of them, I found zero overhead for zones. And there shouldn't be. A process running in a zone does exactly the same thing, instruction by instruction, as that process would perform running on bare metal. When it wants to do I/O, it makes a system call into the kernel. The kernel takes care of that. So there's no extra length to the instruction code path. So there's no overhead. That's how it should be. Hypervisors started out very simple. CP40, it's a very simple hypervisor. Now they're much more complicated, much more feature-rich. That's a good thing, but for most hypervisors, that's new code. They have generated, unless they were able to take code from something else and use it in their hypervisor. Operating systems already had all these features, already had I/O, already had schedulers, already had efficient virtual memory systems. So containers take advantage of those existing mature features. Now, everything that has advantages has disadvantages. And so these are some of the disadvantages of containers. Typically, and especially the first generation of a container implementation uses homogeneous operating system. The container is the same OS as the underlying kernel. You can change that. You can create a translation layer that translates from the guest's system call layer, the top of that layer, to the kernel's system call layer. That's going to introduce some performance overhead, but you can do that. And for zones, we do that for different versions of Solaris. As I mentioned before, there's less isolation for containers. A problem with the kernel could affect multiple containers, but you can mitigate that with some features in the operating system, and of course with load balanced instances. And then, as opposed to the Dark Ages, everything happened. top are all the operating system virtualization technologies that I could find. So all the containers are on top. Just as a reference point, I put all the virtual machine technologies in this time period on the bottom, or at least a good set of them. So this is where it all happened. In the last 15, 16 years, this is when virtualization exploded. I'm not going to go through all of these because Kir's going to help me. So what we're going to do here is we're not going to talk about the VMs very much because this isn't VM days. This is container days. We are going to talk about the top above the line, and we have more time than we were supposed to have. So that's a good thing. So you don't have to talk so fast. We're going to split these up a little bit into. I had to come up with some arbitrary way of dividing them up in roughly half. So I came up with the distinction of the Unix ones versus the non-Unix ones. So Kira is going to come up and talk about the non-Unix ones first, and then I'll come back. I'll give you a break from my voice. I'll come back and talk more about the Unix ones and focus on one in particular. Kira is going to focus on one in particular for these. And then after we have these more or less deep dives, deep, shallow dives, then we'll wrap up the whole session with some conversation about what's happening right now, what's the focus now, and what to expect from the future. So, Kira, we can switch here.
All right. Thanks to the organizers for inviting me all the way. I came all the way from Seattle to do a nested talk. I really like the idea of talk within a talk. What I don't like is I only have like 15 minutes, so let's get started. First of all, my affiliation. I was working for Parallels, and they recently rebranded themselves to Odin. So I work for Odin, and the projects I'm working on are mostly OpenVZ virtual containers and Creo checkpoint restore in user space for Linux. So you know my point of view is a bit skewed towards those. So for Linux, it all started in 1999. Then our chief scientist got that idea that he was inspired by IBM mainframes that were able to do that partitioning Jeff was talking about. And he wanted to do the same inside the operating system, inside the Linux kernel on a different level. The name of that at the time for us was virtual environments, Vs, as opposed to VMs. So basically the same idea, isolated groups of processes running on top of one single kernel. And the other idea was to have a special file system in order to share the code, the binaries and the libraries, and therefore share RAM between containers and make density higher. And the last idea was some resource management to keep the containers within the limits, the isolation basically. And in 2000, we had like 5 engineers working on that, and we made initial public testing of our technology by putting a couple of servers. One was running those virtual environments, the other was running a web front end for those. And we got 5,000 of those VEs on that server at the time. And initial testing revealed that we have really huge problem with resource isolation. So people were running bots, fork bombs, and whatnot, and we had to handle it somehow. So we hired a guy from Moscow State University, a mathematician. MSU is like Stanford here, I think. And this guy wrote a subsystem for Linux called user bin counters. This is basically per group limits. So the problem with Unix and Linux at the time was that all the limits were per process. And in modern age, even a web server is not a process, it's a groups of process. And containers are also groups of process. So there was a need to get the per process group limits. And I think the idea was taken, the user bin counters idea was taken from HPUX, and they had the so-called LUID, and I don't know what L means, but it's basically a group of processes. So he wrote the first implementation of that. And at the same time, prolific Linux kernel contributor Alviro, he implemented the so-called namespace. And now we call it mount namespace. It's basically the same idea as chroot, just with some added bells and whistles, so you can do more with the mount namespace than with chroot. And at that time, it was just called namespace because there were no other namespaces. Later, we did more. So jumping into this century, the next 5 years, I call it Stone Age, we had that good experience with our idea. It worked. So some crazy people in our company decided to implement that for Windows as well. Of course, it's a pretty crazy idea because there's no source code, and you have to basically reverse engineer everything and patch the kernel dynamically. And you even have to do some crazy things, like in the Windows kernel, there's a patch guard that prevents the kernel from being modified, so it has to be hacked around, and this is what they did. And but yeah, they started working in 2001, and in 2004 they made a release. And this Virtuoso for Windows is is still here. We do have that software and we sell it. Also in 2001, another Linux container project was started, and was called Linux vServer, and it's still here, and was started by Jacques Gelinas, and now it's run by Herbert Potzel for the last 13 years, I guess. The only problem with Linux vServer is they don't really want to contribute the code back upstream into the upstream Linux, so it's totally off the mainline project. In 2002, we released the first commercial virtuoso, and we call it 2.0. Also, it's just while I was on the plane from Seattle yesterday, I think I forgot one project that was where, and it's called Meiosis Metacluster. That was some guys from France. What they did is they did live migration for Oracle running on Linux. And for live migration, you need some sort of the container. It's a prerequisite for the live migration. So you don't want a process or groups of processes to disappear out of nowhere. So you make to have it a bit isolated, and this is why container is needed for live migration. So these guys, they have product for that they sold, and it was doing live migration. It was also containers, but just for the for live migration. And they were acquired by IBM in 2005, and I'm not sure, but I believe this team was working on making containers for IBM iX, WPARS, right? Workload partitions. The containers in iX was called workload partition. So in 2004, there was also an interesting project from IBM that's called CKRM, Resource Management Framework, and it was the same idea as user bean counters, basically per group process limits, per process group limits, various limits and guarantees. Unfortunately, this is a demonstration why most of the projects that are developed in-house and then released into public, they don't work. And IBM failed with a few of such projects at that time. They also did enterprise logical volume management system that came out of nowhere and was not accepted into upstream, and then slowly died. And CKRM was another such project. It probably was also over-engineered, but the main problem was that it just appeared out of nowhere, and upstream kernel developers, they don't like things that way. And finally, in 2005, we realized we are also not doing the right thing by having the product closed source. So we have founded OpenVZ as a way to open source our containers technology. And the term container, I believe, Jeff might know better, but the term container appeared at about 2004 or so. I tried to trace it, and the first thing I found it definitely came from Sun, and I thought it's about 2004. So later we renamed our virtual environments into containers. And with the born of OpenVZ project, we started to put stuff upstream, and this is what my next slide is about. So this is the way the stuff is going upstream. Lots of container-related patches were contributed to the Linux kernel. I'm really proud by the fact that our company, we have a kernel team of about 10 engineers, and with our upstreaming efforts, mostly for container-related technologies, we are made into top 10 companies that contribute to code to the Linux kernel. And the other guys there are way bigger. It's like Red Hat, IBM, and guys like that. So So yeah, upstreaming is probably as complicated for developers as this Salmon run. So to the right, you can see the developer trying to push this code upstream, and to the left, you can see a Linux kernel subsystem maintainer. But nevertheless, a lot of code got into. So there appeared a lot of new namespaces. But namespace is probably not the right term for that, because for file system, it's clear that files have names, so the files is a namespace. But for network, for example, the namespace is basically what comprises the network on the Linux server, on the host, on the computer. This is network cards, network interfaces, routing rules, firewall rules, and so on, various network caches and so on. So this is what network namespace is. Basically, when network namespace was merged, Linux got the ability to have isolated domain consisting of devices, routing rules, IP tables, and so on and so forth. That was a result of work of our developers, and they had to write it from scratch, reusing our experience from Virtuoso, but rewriting the code from scratch in order for it to be accepted upstream. Same happened with the PID namespace. PID is process ID, and each container has its own tree of process with its own PIDs, and therefore there's a need for the separate domain, separate realm of the process IDs. And for PID namespace, I believe there were 3 implementations, one from us, another from IBM, and then yet another one from us, and that third one got through and was accepted into upstream. So these 2 are the biggest namespaces. IPC is inter-process communication system 5 IPC that consists of shared memory, message queues, semaphores. And then there is a user namespace, basically an ability to have all the file system and per process UIDs, user IDs, group IDs, and all of that. So in your own container, you have your own IDs. This namespace went in 2007, but it was only completed very recently in 2013. Also in 2006, we opened live migration for OpenVZ. That is a way to take the container from one host and move it to another without shutting it down, without stopping any processes inside. We're migrating all the TCP IP connections and so on. Live migration already existed for VMs, but from the point of view of the underlying thing, that is either a kernel or the hypervisor, VM is much more uniform, so it's way easier to live migrate a VM than to live migrate a container. For container, we have to care about everything, like all the network buffers, all the running process, open files, descriptors, various caches. It's a lot of work. I think that at that time, live migration was like half the code of OpenVZ. Also, another attempt for process group-based management from Google, and unlike IBM, this approach went through. What Google guys did is they take the feature called CPU sets that were used to assign pools of CPUs to pools of processes, and they generalized it. So there was an ability to group the processes, make some process group, hierarchical maybe, and apply some resource controllers to those groups. First, resource control was CPU sets, and then they appear like controllers for I/O limits, memory controllers, like some pretty simple controllers like limit for number of processes in that group, and so on. This is pretty much the same as our user bin counters. It's just unlike user bin counters, C groups made their way to the upstream kernel. So we're switching to that now. Also, all this stuff appeared in the Linux kernel, and therefore LXC tool appeared to make advantage of this new technology. So contrary to what most people think, LXC is not Linux containers. LXC is just a user space tool to employ, to take advantage of those new features in the Linux kernel. I think that's pretty important. And LXC is a tool from IBM. IBM was pretty involved with containers at the time. I don't think they are as involved as they were at the time. Contemporaneity. I had to look this term in the dictionary. Make myself look smarter. So the big part of all containers is resource management. And we had several approaches to that. First of our approach was user bin counters. It controlled everything. It was working fine. It was limiting containers from other containers to not step on each other's toes in terms of resources. It was pretty good. The only problem was it was really hard to configure. 21 interdependent parameters that you should set for each of the containers. So we came with various ways, like written a book about those user bin counters. We written a lot of tools to manage those user bin counter sets. We had sample configs and so on, but it wasn't working really well. Site maybe for people who really read through that big book. So we came up with a second generation of resource management, and it was complete failure. It was simple to configure, but it wasn't working really. So this VSWAP is the third generation resource management that we came up with. It's simple to configure, yet working. It's simple to configure because, as with real hardware or as with hypervisor, you only have two limits, RAM and swap. This is it. I mean, there are also CPU limits, but it's a separate subsystem. Also, in 2010, we came up with ploop. It's basically a container in a file technology, file system in a file, same as for VMs. We found out, previously we were using Truth, and we found out that multiple containers on the same file system is not a good idea because they share the common file system journal, because they share the common characteristics of that file system, because we had to add a per directory quotas to the kernel. So we ended up that ploop technology, which is a file system in a file with some bells and whistles. Also, in 2011, we came up with CREW. This is checkpoint and restore in user space. The problem, it's the same problem as was shown on my photo of grizzly bears and salmons. Basically, our in-kernel checkpoint restore is a very, very complex thing, and we tried to merge it upstream to no avail because it was touching each and every subsystem with our code, and no maintainer wanted that. So other guys were also trying to merge checkpoint restore in the Linux kernel, and they also failed. I know a guy who spent like 3 years of his life doing exactly that, trying to merge checkpoint restore to the Linux kernel. And he also failed, and we also failed. So we circumvented the system by doing most of the checkpoint restore work in user space, with the kernel exporting some mechanisms for that. So for example, for most of the stuff that's happening to processes in Linux, you can get it from /proc. You can get some stuff about the processes by using some debug facilities like ptrace. You can get some stuff from inside the process itself. We're using all those mechanisms and more to get the image of the running processes and save it into a dump file. And we use some other mechanisms to restore that later. So this this is a prerequisite to the live migration. Checkpoint the processes and then restore it on the different machines. Also, during that time, 2 years ago, plenty of new container projects appears. Of that, I would like to mention Docker, Core OS, and Google LMCFCDFY. Let me contain that for you. That's the name of the project. In 2014, we got crew working for Docker and LXC, and I think it's just recently that Docker merged our support for crew, so you can now Docker checkpoint and Docker restore. And finally, just this year, we realized that we are doing OpenVZ all wrong. It's open source, but the process itself is closed source. So we doing a reborn of OpenVZ with new development model, with everything happening in public, with more code available, with more repositories available, with our developers sitting in the same room, but they're talking through the mailing list, through a public mailing list, which you can read and you can talk to them too. And it's just a few words for the future. It's 15 years of history, but we're not done yet. That Virtuoso.7 is our future OpenVZ that they're working on right now. And we actually invented yet another generation of resource management, this time with a user space daemon helping and adding our resource management will become more dynamic with bursts, guarantees over time. And we'll probably do proper port to Power and ARM architectures, because the improper port, I did that like 10 years ago because the technology, containers technology, is architecture independent. And therefore, it's very easy to port to various architectures, unlike VMs that require deep understanding of the architecture, CPU, and so on. So for Creo, we have a sub-project of Creo called P-Hole. This is the project for live migration, because Creo doesn't care about live migration. It's only about checkpoint and restore. And with Creo, we want to integrate this into many, many different things. There are some other projects that we're working on. They maybe come through or not. I don't know. But I have a talk tomorrow, and I'll be talking about these things in more details tomorrow. And today, this is as much as I can do. Thank you so much.
All right, last section. We're in the home stretch here. History takes a long time. That's why they call it history. So a quick run through on the of containers in the Unix space, and then I'll talk about the application of those 5.3 laws to one of these. The one that I know best, apparently well enough to write part of the book. So it's, in the Unix space, this started off with FreeBSD jails back in 1999, 2000, somewhere in there. It's a good implementation of containers, provided isolation of processes, file system, a couple of other things, some administration delegation, but it was weak in some isolation, some areas of isolation, such as networking. Shared network stack for all the jails. So good. Then 2005, Sun released Solaris Zones. That was I call it a very complete implementation with one section, one of those things missing, which we addressed 3 years later. So Solaris Zones had a complete separation of namespace per zone. So each zone had its own root directory and all the files under /etc and all those things. Per zone users per zone, permissions, privileges. I'll talk more about those in a couple of slides. And that was January 2005 that Sun released that. HPUX had a resource management piece as Solaris had. It was Solaris Resource Manager from a long time ago. HPUX has a similar resource manager called SRP, Secure Resource Partitions, for resource management, but no namespace isolation. So they addressed that in around 2007 with HPUX SRP v2, which offered that namespace isolation. Closely followed by, and this is, I think this is where the containers word comes from, but I haven't found anything else to prove it. When, with Solaris, we merged the namespace part of zones and the resource manager features together to add that other requirement of virtualization, we renamed that to be containers. And so you see Solaris containers. And that stayed around for quite a while. So in the book, we decided to stick with the phrase Solaris containers and not confuse people with Solaris zones, even though our marketing people would confuse them. So we used containers, and that stuck around until 2011. So that was after the acquisition of Sun, when we decided this using Solaris zones and Solaris containers, when it's basically the same thing, was just too confusing. So we dropped the word containers and stuck with the first term, Solaris zones. So it's kind of ironic there that we dropped it with the word containers, and even though it had become common usage. 2008, IBM came out with AIX workload partitions, WPARs, basically a clone of zones. The features, they all line up. They did have some additional features that they had that Solaris zones didn't, which is good for them. HPUX then, 2011, in one of the 11i releases, one of the updates, they came out with namespace isolation to add to their secure resource partitions. And then they renamed that to be system containers. They also offered HP 9000 containers, which is kind of interesting. That's a HPUX container, but to run old previous architecture HP 9000 code, which required binary emulation, real time. And you can guess what happens to the performance when you do binary translation in real time. And then I put this here because the newest thing we released last year with Solaris 11.2 was kernel zones. This is a deviation from containers. It's neither a container nor a virtual machine, so I put it straddling the line to indicate that with a little arrow. The kernel zone, I'll talk more about this later, but it has its own kernel running in a container on top of the container for the kernel for the system, which offers some more flexibility. So in some ways, and there's even a marketing thing which says that, but yes, the Solaris 11 kernel acts in some ways as a hypervisor. And so I have part of it below the line. It's hard to then define. So I thought it would be interesting to apply those original 5 degree laws to one of these technologies. And the one that was easy for me to do was zones. So I'm going to take a few minutes and do that. So this is the same things as before, but filled out with how it's applied. Equivalence. The program running, as I mentioned before, for performance overhead, the program running in a zone runs exactly the same as it does not in a zone. No difference at all. In fact, it's hard to tell that you're in a zone. We didn't try to hide it. It's not like that. But you have to know the couple of commands that will then give you the output that will essentially tell you, oh yeah, you're running in a zone. That's how transparent it is. Resource controls, of course, I mentioned the resource controls that came from Solaris Resource Manager. I'll talk a little bit more about those in another slide. As I mentioned before, there's no software layer between a process running in a zone and the kernel, so there's no performance overhead. Solaris 10 added to Solaris something called privileges. This is fine-grained privileges. In the old, in most Unixes and Unix things that are sort of like Unix in some way, there's this root user, and the root user can do anything. And that's good if there's a very small number of root users. But big companies that want accountability and need to give multiple people the ability to manage a machine, they want something in the log file that says something besides the root user logged in. Well, who is that? I need to know who to blame for what the FCC is coming after me for, or the SEC. So they asked us years ago to make this different, to get rid of the root user. So for Solaris 11, there is no root user. There's a root role. So a person logs in and can then, if given access to certain of these privileges, can use those privileges to do very specific things. So you can have a normal user who has the ability to modify the system time clock and change it to an hour ago or an hour from now. But that's the only thing that the root user normally could do that user can do. And there's about 50 different privileges. And we went through the code and looked for all the places where it said, if UID equals 0, then allow this. Now it says, if this user has this privilege, then allow that. Sure. Yeah. So we did that with zones. So a zone can have any set of those privileges with the exception of a few that zones can't have. There's a default safe set, and you can increase that or decrease that. I'll talk a little bit more about that. And like I mentioned before, when you install Solaris, you have what's called the global zone. That's the normal Unix-like environment. And all the other zones are called non-global zones. There's some variations there. But from the global zone, a person with sufficient privileges can see into any of the processes in any of the zones. That's very useful when troubleshooting problems. So these are these 5 things. They're core pieces of zones or containers. I have a very long blog that's been going on for many years. There's a lot of stuff about Solaris Zones in there. So if you want, you can go check that out. So I mentioned those privileges, these fine-grained abilities. Here's the one that allows you to modify the system time clock. Here's one that allows you to be an SMB server. So you can create a zone that serves up files to Microsoft Windows clients out there on the network, or a zone that's the NFS server. You can have lots of these things. I booted 1,000 zones on an 8-core system about 6 years ago, and it was kind of interesting. That's also in my blog. So these privileges define the security boundary around the zone. By default, it's very safe. We don't have any record of security issues with someone breaking out of a zone or into a zone. But you can tailor that. You can add privileges, so you can give a zone this privilege for the time clock and make that zone the only one that's able to modify the system time clock for all of the system and all the zones. That might be connected to the web and to some NTP server out there to go get the sense of time and set it for the whole system. If you do that, you probably want to take away other privileges because that's a web-facing, directly connected to the web. This set of privileges is configurable, so you can change it later on if you want to, if you decide the security is too loose or too tight. Also, to demonstrate the secureness of a zone, back in the Solaris 8 days, about 15 years ago, we had this version of Solaris 8 called Trusted Solaris 8, which set up data compartmentalization. The U.S. government, intelligence agencies, Department of Defense, they need to have a computer that has the area where the secret data is and the top secret data is and other classification labels that I'm not allowed to know about because I don't have a security clearance. And we used to do that with Trusted Solaris 8 in a certain way that was very, very finely tuned, but was hard to move forward, so there was no Trusted Solaris 9. For Solaris 10, we used zones to do this. So a zone is a top secret zone. Another zone is the secret zone. Different levels of compartmentalization. And you can't even copy and paste on a workstation from one window that's top secret into another one that's only secret. It's not allowed by the kernel. So we do this for them. And they trust the security of zones to separate that data. So that sounds to me like it's pretty secure. And if you have security needs that are greater than that, I don't want to know about it. Sure. Oh, Thank you. All right, I'll be quick. Sorry about that. So as I mentioned in the beginning, namespace, we've gone over that quite a bit. Lots of file system choices for zones. So you can share data or have isolated data. That's your choice. You can make a zone read-only. So all the Solaris content itself cannot be modified, no matter what privileges you have in the zone. That prevents Trojan horses. In Solaris 11, we also added a bunch of network virtualization features. So we have virtual NICs, virtual switches, what are essentially virtual routers, but a virtual router is just a zone with 2 virtual NICs and routing turned on, and then you do whatever you want inside there, which also has load balancing and NAT and firewall features. So you can create a zone that's a firewall. One side goes out, one side goes into all your zones on the inside that themselves don't have any network connection to the outside. Even an elastic virtual switch, so layer 2 switch that spans multiple computers, and the different zones and the different computers can connect to this switch, and they all think they're on the same switch, which has interesting availability characteristics. With all this, you can build any arbitrary network structure with IP addresses. You take a physical network and put it inside of a Solaris system with different zones for the different workloads. More security features like IP and MAC address spoof prevention. Lots of resource controls. I wish I had more time to talk about them, but partitioning of CPUs, accounting caps on CPU time. There's a fair share scheduler that's been in there forever. RAM caps, VM caps, all these things part of resource management to make sure that one zone doesn't take over a system and use more resources than it should. We also have what we call non-native zones. So those kernel zones I mentioned with a separate kernel level, separate patch level for that kernel than the underlying one. And the layer between them is very clean. So when Solaris 11.3 comes out, you can run a Solaris 11.3 kernel zone on top of a Solaris 11.2 kernel, which is sort of backwards in the compatibility context. You can run Solaris 10 zones in a Solaris 11 system, so old workloads can move forward and then still use the Solaris 11 features like network virtualization and transparent encryption. So that was way too fast, but I hope that helped understand some of the ways that you can implement those 5 laws. So what's happening now, the virtualization, creating virtualization has largely matured. We're still seeing some things come out, Microsoft containers, Windows containers, those sorts of things. But we are also moving forward into the next phase of virtualization. Okay, now I've got 1,000 Solaris zones on one Solaris system. How do I manage that? Managing 1,000 computers is hard. It's not all that much easier inside of one system. So we see things like Op Center, which could manage both zones and Spark logical domains. We see OpenStack with its ability to, we're getting there with that, but its ability to manage large sets and easily provision new workloads in the right kind of environment. Docker, which solves a similar problem, is part of this. And this is early enough here that I expect a lot more in this space. And hope to learn more about this in the near future. So, thank you. Thank you, Kir. Thank you, Andrew. If you have any questions, I'll be wandering around, probably having some of the snacks.